Good evening, everyone. Welcome to the last day of our FDP sessions on artificial intelligence and machine learning. Right. So as part of this session, we are going to learn an important algorithm which is part of deep learning, which is called as artificial neural network. So we'll quickly recap what we have covered in the last session. In the last session, we understood what exactly is machine learning. Right. Under machine learning, we understood the types, the three types: supervised, unsupervised, and reinforcement learning. And we have understood an unsupervised learning algorithm. What it is? It is KNN, K nearest neighbors. Where do we generally use supervised algorithms? We use supervised algorithms when we are working on the data which has Y column, the target column. If there is output in the data, we use supervised algorithms. Right? Yes. So as part of supervised, again, there are two types. The first one is classification and the next one is regression. Classification algorithms and regression algorithms. KNN can be used for both classification and regression algorithms. Either the data is discrete, if the values in the Y column are discrete, or if the values in the Y column are continuous, we can go and use KNN algorithm. It is a shallow technique. It is a shallow technique. And we also understood ML primer. As part of ML primer, the flow that we have discussed, in which we initially split the data into two parts, train and test. Then on the train data, using the train data, we build the model. The model, after getting trained, we use it for the test data. We'll get the predictions. We compare the predictions and the actual, we'll get the test accuracy. And this test accuracy, apart from it, we also get the train accuracy. If I do the same thing on the train data, and these two get compared. We compare both train and test accuracies and we'll decide the fit of the model. Either the model is right fit, underfit, or overfit. Right? Yes. And as usual, we understood the concept of KNN, how KNN works. KNN works on the logic of distance. It uses distance formula, distance logic, and there is no kind of training guys. That is why it is called as lazy learning algorithm. And we have multiple distance metrics that can be considered. Euclidean, Minkowski, Manhattan, cosine based similarity. Okay. So in this way, there are multiple distance based metrics which can be used as part of KNN algorithm. And we have also implemented KNN on a data set. We have implemented KNN on the data set. Right. So without no further delay, let us start today's class where we will be learning an important fundamental algorithm. It is artificial neural network. Artificial neural network. In short, it is named as ANN. Artificial neural network. So this artificial neural network is the base of, the entire AI, whatever we are using. In today, okay, it might be GPT, Chat GPT, Google Gemini. All of these are different transformers. What is a transformer? Transformer is again a neural network, guys. Okay. So if you are clear on the concepts of artificial neural network, you can start learning the types of neural networks. There are multiple types of neural networks. And For all these different types of neural networks, the foundation, the fundamental concept is ANN. So let me start. But before that, let us fix the agenda. What exactly are we going to cover as part of this session? The final day is, initially we'll understand what is deep learning. Okay. Like how we have understood what is machine learning, we'll understand what is deep learning. Then we'll get introduced to neural networks. So what exactly does a neural network contain? Okay. Then the architecture of neural network, followed by some core concepts, fundamental concepts in neural network called weights, bias, activation functions, loss functions. Okay. And we also have a concept called optimizers. Okay. What is the purpose of optimizer? How do they work? We'll understand. And one of the widely used optimizer is gradient descent. We'll understand how gradient descent works. And finally, we'll understand types of ANN, different types of artificial neural networks. And post understanding the concept of ANN, we'll also implement ANN on a data set, guys. We'll take a use case and we'll implement ANN on this data set. I hope it is clear. Okay. So whatever we have done earlier, in the same way, we are going to today understand the concept of ANN, artificial neural network. So let us get started. And what exactly is deep learning? Probably you might have observed this Venn diagram. In order to understand artificial intelligence, machine learning, deep learning, you might have observed this Venn diagram, right? So where machine learning is a subset of artificial intelligence, deep learning is subset of machine learning. So it is a subset, a subfield of machine learning which uses the concept of neural networks. In deep learning, we use neural networks. What does these networks, neural networks contain are, they contain multiple layers. They have multiple layers. Okay. So because of these layers, they help us to understand the complex patterns in the data. So within the data, there are some patterns. Even though if the patterns are complex, we are still able to understand, the model is still able to understand because of these layers. And it is actually inspired from the human brain. Because within the human brain, we'll have neurons. Yes. So based on the structure and the functioning of human brain, okay, so the concepts of neural networks were being structured. Especially, how the neurons get connected. In the same way, within the neural networks, we'll also observe that the neurons getting connected with each other. So in short, deep learning is a subset of machine learning which uses the concepts of neural networks and that tries to mimic human brains. That tries to mimic brains of the humans. Right? So let us understand what are neural networks. What are neural networks? Because we know what is a neuron. Probably if you remember, in your 8th standard or 9th standard, you might have learned the concept of neuron in biology. So is this the neuron? The structure of neuron. But this is the neuron that we have within the human body. Right? So we have dendrites for connection and this is the stem, so on, right? So this is a biological neuron. But a neural network is a network. It is a network in which it has neurons. It contains neurons, but they're not biological neurons. They are artificial neurons. You see here, they are artificial neurons. But in the same image to the left side, you see a biological neuron. And these neurons, the neural networks are again inspired from the structure and the functioning of human brain waves. What exactly does this neural network contains is it is connected with the layers. Each and every neurons get connected with some layers. So a neural network contains especially three layers. What are they? Input layer, hidden layers, and output layer. I repeat, a neural network contains input layer, hidden layers, and output layer. Okay, so within a neural network, we can have only one input layer, but multiple hidden layers. And these hidden layers are actually, they are responsible for, capturing the patterns from the data. These hidden layer neurons that we see here, they are responsible for capturing the patterns from the data and only one output layer. Again, the question raises, okay, if I assume that if there are three hidden layers, within these three hidden layers, how many neurons should I have? Again, that is the hyperparameter case. We try experimenting with the different number of neurons within these hidden layers. Okay, so let us understand these layers to the core, to the depth, one by one. What is the purpose of input layer followed by hidden layers and output layer? So within the neural network, we'll have three layers. They are input layer, hidden layer, and output layer. So whatever you see, these circles are called within the input layer. These are called nodes. These are called nodes. So we pass input values to these nodes. X1, X2, X3, X4. Assume that I have 4 inputs. Okay, so in my data there are 4 inputs. So each and every input will be passed one by one. Okay, to these nodes. I hope it is clear. Okay, if you take an image, it represents pixels. And why neural networks became popular is it can work on both structured and unstructured data. It can work on both structured and unstructured data. Either you take structured, that is the data which can be represented in the form of tables with the predefined schema. Okay, they are called structured. That is called structured data. And coming to unstructured data, the raw data which cannot be represented in a table is called unstructured data. And the examples are images, videos, text, speech. All of these are examples of unstructured data. So either my data is structured or unstructured, neural networks can work on any type of data base. If it is structured data, it takes features. The input node takes the values of features. If it is unstructured data, like text or images, so we can represent image in the form of pixels. So the pixel values need to be passed. We'll pass pixel values. I hope it is clear. Then, what does these hidden layers do? Within the hidden layers, they're actually between input layer and the output layer. See? They are between input and output layer. And each neuron in these layers, in these hidden layers, these are called neurons. Neuron 1, neuron 2, neuron 3. Again, your question might be raised. Why only 3 neurons? No. It is not that question that you might raise. Should we go with every time 3 neurons? Not exactly. This is the number of neurons within the hidden layer is a hyperparameter. It's a hyperparameter. We change, we experiment. Okay, and the number of hidden layers to be used within the neural network is again an experiment, guys. It's a hyperparameter. Okay, it's not like just we use only one hidden layer every time. No. As an example, we are trying to understand a basic neural network here. A basic neural network we are trying to understand, in which I used only one hidden layer. That doesn't mean every time we'll go with one hidden layer. I can also go with n number of hidden layers. And within these hidden layers, the number of neurons might change. Yes. And what does these neurons do? These are called neurons. Okay. So these are not actually called neurons. Within the input layer, whatever you see, they are called nodes. And the circles, what you see in input, hidden and output layer are called neurons. Because within these neurons, there are a lot of calculations that were being done in the backend. Okay. On the values that you pass, there are a lot of calculations, computations will be done. Clear? So what kind of calculations? We'll understand. What exactly happens, how the data, how the values from the input layer to the hidden layer gets passed. We'll understand one by one. And finally coming to the output layer. Output layer is actually responsible for producing the output. Either it can do a classification task as well as a regression task also. Whatever might be the task, irrespective of the task, it produces the output. Okay, and the number of neurons in this output layer depends on the task. Okay, if it is a regression case, we'll just go with one neuron. If it is a classification task, okay, again, if it is a binary classification, we'll go with one. One is enough. But multi-classification will have multiple neurons, guys. I hope it is clear. So now let us understand what exactly happens, how a neural network gets trained, the working principle of a neural network. Let us focus on it. Okay, before that we have a few core components of neural networks. They are called weights. They are called weights, bias, activation function, and loss function. But where do we use these? Is within neural networks only. Till now we did not discuss them. But these are the key components of neural networks. The reason why they are called as key components is they decide actually the output. When you are changing these values, when you change the activation function, obviously your output will change. Okay, so what exactly are weights? Weights are nothing but the values. Okay, the values that each neuron, each connection has. Okay, between two neurons, you'll have a connection in this way. So I assume this is my neural network. Okay, and I'm trying to draw a fully connected network, guys. A fully connected network is a network in which, all the neurons from the previous layer gets connected to the next layer. That is called a fully connected neural network. This is a fully connected neural network. See, every neuron present in the previous layer, it got connected to the every neuron present in the next layer. So it is a fully connected neural network. So what exactly weights mean? Weights are nothing but, between the neurons, you see a connection. Yes. So each connection between the neurons will hold a weight, will hold a weight. And this weight will actually determine the strength of the connection. But how are these? Who is actually giving these values for weights? Okay, that part we'll understand. And coming to bias is an additional parameter, that we add to each and every neuron, okay, which helps us to, get the weighted sum of the inputs. And finally, we also have activation function. In order to understand activation function, we have to understand what exactly is activation function. But before that, let us understand what do we have in a neuron. Assume this is a neuron, guys. Assume I took only a single neuron. Within a neuron, we'll have two components. We'll have two parts. The first one is called summation function, and the second one is called activation function. Within a neuron, we'll have two parts. The first part will be summation function, and the second part will be activation function. What is this summation function? Summation function is nothing but it takes whatever the connections that neuron has, it sums up all the product values of the values, the input values multiplied with the weights. So I'll give the formula here. For summation function, the formula is given as xi multiplied by wi plus bi, where I takes from 1 till n. Now let us understand this formula first of all. So if you see here, this particular neuron has connections from the three input layers. Within the input layer, there are three nodes, right? So from these three nodes, we have the connections to the same neuron, right? So the input values get multiplied with these weights. The input values gets multiplied with the corresponding weights, okay? And the bias that get initialized gets summed up, and this will be the, this is what happens in summation function. And this output of summation function will be passed to the activation function. And what is the purpose of activation function? The activation function introduces nonlinearity. Because of this nonlinearity, the neural network starts understanding the complex patterns. Commonly used activation functions are ReLU, sigmoid, tanh, softmax. Then we also have different types of ReLU. Leaky ReLU, ELU, PLU, so on. There are multiple activation functions. And we are also going to understand activation functions to the depth. And finally, loss function. What is loss function? It is nothing but the difference of the predicted minus actual. The difference between predicted and actual for one single record is loss function. It is loss function. And there are, again, commonly used loss functions. Mean squared error for regression, mean entropy loss for classification. Okay, so what are these loss functions? There is also a concept called cost function. Okay, so let us understand this loss function and cost function, and the commonly used loss and cost functions in the next couple of minutes. But we have to understand how a neural network works. Okay, we have to understand how a neural network works. So neural network working principle is actually in two steps. There are two steps. One is called forward propagation and the next one is called backward propagation. Forward propagation and backward propagation. So what exactly happens in forward propagation and what happens in backward propagation? Let us understand this. I'll take a small neural network. So I assume this is my neural network. What is this? This becomes my input layer. And this represents hidden layer neurons. And this represents output layer neuron. The nodes from the input layer, they got connected to the hidden layer neuron. And from the hidden layer neuron, it got connected to the output layer. And the output layer neuron is responsible of, producing the output. This is what happens. So assume I took a small neural network. What I have to do initially, I have to pass values to my input layer nodes. Input layer nodes. Guys, these are not neurons. Within the input layer, we'll have nodes. But in hidden layer and in output layer, we'll have neurons. Because if it is a neuron, it should contain two parts. What are they? Summation function and activation function. But will not have any kind of summation and activation functions in input layer neurons. No, that is why these are called nodes, which accepts the values. We pass the values of our data, okay, one by one, and the weights gets assigned randomly. W1, W2, W3. The input data that we pass through the input layer neurons, okay, gets multiplied with the weights that get assigned randomly. W1, W2, W3 are weights. Each connection between the neurons have weights. How are they initialized? They are initialized randomly. Okay. So once if the weights are initialized, the first component in the neuron of hidden layer is summation function. Yes. This summation function, uses the formula summation of xi wi plus bi, where I takes from 1 till n. I takes from 1 till n. Okay, so what exactly happens is x1 will be multiplied with w1, x2 will be multiplied with w2, x3 will be multiplied with w3, and the bias for this neuron gets initialized again randomly. All these values gets summed up. All these values we are summing up. Okay, so this value will be the output for activation function. So activation function will take the output from summation function. Whatever the weighted sum that we get calculated, that will be passed as input for activation function. And these activation functions, they are responsible for adding non-linearity to this neural network. And they help us to identify the patterns, understand the complex patterns in the data. Okay. And once after getting the output again, there is a connection between hidden layer neuron and output layer neuron. So a weight gets initialized. So the output from the activation function will get multiplied with the weight of, this weight between these two neurons, and that will be given as, That will be done as part of summation function. Again, within this neuron, you'll have two parts, summation activation. So a bias should be initialized B2 and that will be returning as an output. A predicted value, it will produce an output. So this entire process is called forward propagation. This is called forward propagation. You are going from input layer to the output layer. So this is what happens as part of forward propagation. Guys, I took a small neural network, right? So if you are just imagine, just map with a huge or a big neural network where you can have multiple hidden layers. Within these hidden layers, you can have multiple neurons, but the process will be same. The process will not change, right? So once after getting this predicted value, what happens? We also have the actual value. Yes, we'll also have the actual value. So the loss function gets calculated. What is loss? Y minus y hat. When you calculate y minus y hat, you'll get the loss value calculated. The error get calculated. Okay. So your model may not predict the value as it is initially. So then the step 2 starts, which is called back propagation. That means from output layer, it starts going back in the reverse direction. This is called back propagation. During back propagation, what exactly happens is the weights and the bias that got initialized randomly gets updated. Okay, in order to minimize this loss, see how I can minimize this loss. When y is actually y hat, when the predicted value is my actual value, only then I can say the loss is 0. Right? Obviously. So in order to minimize this loss, the model starts backpropagating. What exactly happens in backpropagation is the weights and the bias W1, W2, W3, W4, B1, B2, the parameters. Okay, so all these parameters need to be updated, guys. They need to be updated, and that will be done as part of backpropagation. They will be updated using a formula, and that formula we have it here. What is the formula says? New weight is equals to old weight minus learning rate, which is represented with neta, which is represented with eta. Okay, multiplied with derivative. Multiplied with derivative. So I'll keep the formula here. W old is equals to, sorry, W new weight is equals to old weight minus eta multiplied by derivative of loss divided by derivative of old weight. Derivative of old weight. So what's happening is old weights that we have, these old weights will be updated so that the new weights gets calculated. Once after calculating the new weights, in the same way, using the same formula, the bias also get updated. The bias also get updated, and these bias, once after having the new bias and the new weights, again the model starts forward propagating. It propagates forward direction. It repeats the same process, guys. Okay, when it repeats the same process, again you'll get a y cap, the predicted value. Again you'll calculate loss. So this journey continues until where? Until the loss reaches global minima. What is this global minima? You'll understand. As part of optimizer, we'll discuss what exactly is global minima. Okay, so this is what happens as part of neural network. And one forward propagation and one backward propagation is called one epoch. It is called one epoch. I repeat, if the weights are getting updated once, it is called an epoch. So we'll discuss this what exactly epoch means as part of use case. Because under use case, we'll use this parameter called epoch. Right? Yes. I hope you guys have understood the concept of working principle, how neural network gets work. Now let us understand the weights and the bias. How are they getting initialized? Because we came to know in the first iteration, okay, under the first iteration, both weights and bias are actually randomly assigned. Yes. How are they randomly assigned? Now let us understand this. If you see here, I have a neural network. I have a neural network in which this is my input layer, hidden layer, and output layer. So within this input layer, you see how many nodes? Two nodes, x1, x2. I am passing x1 and x2. And these two nodes are connected with two neurons. And this is a fully connected neural network. The reason being, each and every neuron, it got connected to the every neuron present in the next layer. Right? So what I'm doing here is, if you see here, observe, properly observe guys. What exactly are weights? Weights are nothing but the parameters within this neural network. Okay, they are actually helping us to transform the input data, whatever the input that we pass. Okay, the input values, they are actually, transforming these values. The weights are transforming the input values and they are carrying to the next layers. Right? And between two neurons, if there is a connection, for sure it will be associated with a weight. Yes. What is the role of weights? They determine the strength between the connection of neurons. Yes. And how are they initialized? Is they are randomly initialized, but we also have other techniques to initialize weights. We use Gaussian distribution to initialize weights. He initialization, Xavier initialization. Okay, there are different techniques to initialize weights gives. So the weights gets initialized upon the technique that we select. But in general, they are initialized randomly. Then coming to the bias, what exactly bias does? They help them, it allows the activation function to shift either left or right. Because what if sometimes, see the weights that were initialized, if they are 0, or if the input values are 0, assume. Okay, so we know that the formula that summation function uses is xi multiplied by wi plus bi. Xi multiplied by wi plus bi. If the inputs or the weights, if they are initialized are 0, this product will be 0. Yes. So even though if the product is 0, the bias that gets initialized will have some value so that it will not make this neuron die. If bias is also 0, what happens? If there is no kind of information, if this is 0 and this is 0, obviously my output is also 0. Yes. So what kind of information you are passing here? It will be 0. So if it is 0, then obviously the output will be 0, right? There is no kind of information getting passed. Because of this bias parameter makes, it allows the activation function to shift either left or right. And how are they initialized? It uses the same concepts for initialization. If you observe here, okay, and these are some of questions that will be asked in interviews. Input layer and hidden layer, right? So between input layer and hidden layer, tell me the size of weight matrix is what? Okay, tell me the dimensions for weight matrix will be a questions. In short, you can tell, you can remember in this way. How many nodes you see in the previous layer? 2. And how many neurons you see in the next layer? 2. So obviously you'll find 4 weights. 4 weights gets initialized. See. But bias will be only 2 guys. Why bias will be 2? For one neuron, only one bias will be initialized. So how many neurons you see here? Only 2. So obviously number of bias gets initialized will be 2. If you go to the next layer, tell me the weight matrix. It will be 2 multiplied by 1. 2 in the hidden layer, 1 neuron in the output layer. So obviously 2 weights will be initialized. W21 and W22. But bias will only be 1. So in this way you can remember, because we'll again recap this as part of our use case. And next to weights and bias, let us understand activation functions that will be used. What is the purpose of activation functions is, activation functions are nothing but mathematical functions. You know, what are these activation functions? They are nothing but mathematical function. If you take a summation function is given, what is the formula? Summation of xi wi plus bi. So is this a mathematical equation? Yes. In the same way, activation functions are also mathematical functions. Okay, which are applied to the output of each neuron. So the output of summation function will be passed to activation function input. Activation function will take this as an input. Okay, so this z will be passed as an input for activation function. And these activation functions are actually introducing non-linearity to the model. Because of these activation functions, the neural network starts learning complex patterns. What if these activation functions are not there? Assume if these activation functions are not there. You know, earlier our scientists even have tried without activation functions. Earlier there is no activation function. That time, you know, our neural networks was similar to regression models, linear regression. What is the equation for linear regression, guys? Beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus so on, error term, or beta naught, the coefficient. Is this same as summation function equation? Yes. So without activation functions, our statisticians, scientists, all of them, they have identified they are similar to linear regression models. Okay, so that is why activation functions were being introduced. What are these activation functions? They are nothing but mathematical functions. And you know, without these activation functions, the neural network cannot learn complex patterns. They introduce nonlinearity. They determine output at each neuron. And they can also control gradient flow. What is this gradient flow? We'll understand, guys. Hardly in the next 5 to 10 minutes, each and every, you know, technical word that we are discussing will be clear. Okay? Right. So let us start understanding types of activation functions. Activation functions are of two types, guys. Activation functions are of two types. Linear activation function and non-linear activation function. We generally will not use linear activation function. Okay, we'll not generally use linear activation function, but still we have to learn linear activation functions, right? So let us understand. If you see here, this is the graph of linear activation function, which is, resembling a straight line. What does it mean? F of x is nothing but x. Whatever x value pass, that will be given as output. If I pass 0, I'll get 0. If I pass 8, I'll get 8. If I pass minus 8, I'll get minus 8. So this is a linear activation function. Okay. So what is the range of linear activation function? Minus infinity to plus infinity. If I pass 100, I'll get 100 as my output. If I pass 10,000 or minus 10,000, I'll get minus 10,000 as output. The function says f of x is equals to x. Right? So, we generally will not use linear activation function. Will not use linear activation function. Then, what activation functions we use are non-linear activation functions, guys. We use non-linear activation functions. So let us understand one by one non-linear activation functions and their advantages as well as limitations. The first non-linear activation function that was introduced is sigmoid function. It is sigmoid function. Yes, the sigmoid function that we have understood as part of logistic regression. Okay, so under logistic regression, we use this sigmoid function. Okay, which is like similar to an S-shaped curve. You see here, the curve is similar to S-shape. And the sigmoid function uses the formula 1 by 1 plus e power minus x. 1 by 1 plus e power minus x. So in this case, it will be 1 by 1 plus e power minus z. Because z is nothing but the output that we get from summation function. So that value will be passed here and you'll get the output from 0 to 1. The output will be between 0 to 1 only, guys. Where do we use these sigmoid functions? This sigmoid function activation function is generally used in binary class classification task. If I want to, if I'm working on a classification task and if I want to go with the binary class, there I go and use sigmoid function. Activation function, sigmoid function will be used in output layer neuron. So within the last output layer, the activation function will be sigmoid function. Why? The output will be only between 0 and 1. Okay. So I'll keep the threshold. If the value is less than 0.5, give it as class 1. If the value is greater than 0.5, I'll keep it as the output should be class 2. So that is why sigmoid function is used as activation function in output layer neurons. What if sigmoid function is used in hidden layer neurons? Within the hidden layers, okay, if sigmoid function is used, there we have two problems. One is called vanishing gradient problem. Very, very, very important, guys. Vanishing gradient. What is this vanishing gradient problem says is, For this, I have to go and, write the formula of back propagation for the new weights. W new is equals to W old minus eta multiplied by derivative of loss divided by derivative of old weight. Right? So when the model is in backward propagation, it tries to update the weights bias using this formula. Yes. So when it uses the formula, it has to calculate this gradient. This part is called gradient. Derivative of loss divided by derivative of old weight. So if this value is very small, okay, if this value is very small, okay, this is called learning rate. This is called learning rate, which is typically 0.001. Okay, so when you multiply two small values, you'll get very small value. Yes, which is obviously 0. This value, what's happening? It will be 0. Right? So when you try to remember, when you try to remove 0 from old weight, what will be? The output will be again old weight only. So what it is happening exactly here? Even the new weight will be same as old weight. So what's happening? I can understand the weights are not getting updated. This is because of, the gradient is getting vanished. This is, an important topic in ANN. Vanishing gradient problem. Why do we get vanishing gradient problem is the gradient that we try to calculate gets vanished. Okay. When you are working on a very complex neural network, it uses the concepts of chain rule. It uses the concepts of chain rule to calculate this gradient value. So as part of this backward propagation in chain rule, the output for this gradient will be 0. So 0 multiplied by anything will be 0. Again, there is no update as per the weights. Because of that, I can see the weights are not getting updated. All is this because of the gradient becoming vanished. See. And this problem was identified in sigmoid function, guys. This was identified in sigmoid function. You know why? This is because of when you take the derivative of this function. I hope you remember the derivatives. Calculus. Okay, I'm not going to teach calculus and all, but if I take this derivative of this particular sigmoid function, the range of this sigmoid function derivative is only between 0 to 0.25. Okay, so 0 to 0.25, when you try to calculate the values, again they become very small. Okay, when you multiply these values as part of chain rule, you'll get the values being very small. So that is why the new weights will not be updated. The new weights will not be updated where it takes the same old weights. So when it will be same way old weights, we cannot make our loss reaching to global minima. No. And moreover, sigmoid function is not zero centered. If you see here, is it zero centered exactly? No. Right? So these are the two limitations that were being observed with respect to sigmoid function. Okay. So then what our statisticians have done is they have come up with one more activation function called tan h. It is tan h activation function. So let me show you the plot. So this is the plot of tan h activation function. So it uses the formula e power x minus e power minus x divided by e power x plus e power minus x. So I have earlier discussed, right? Activation functions are nothing but mathematical functions. The function for tan h is e power x minus e power minus x divided by e power x plus e power minus x. And the range is between -1 to +1. So between -1 to +1, you'll have the output. The output of tan h function. And the problems that tan h function raises are still the vanishing gradient is still existing with tan h function also. The vanishing gradient problem that we have discussed earlier is not, tan h is not solving this vanishing gradient problem, because when you try to take the derivative of this function, you'll get the output between 0 to 1. You'll get the output between 0 to 1. So still the vanishing gradient problem exists with tan h function. That is why tan h cannot be used in the hidden layers. In the hidden layer neurons, tan h activation function is not preferred. But the advantage of tan h activation function is it is zero centered. So if you see here, exactly it is zero centered, which helps us for faster convergence. During the training, the laws that we have initialized, the laws that we have calculated can be converged faster during the training journey. And the limitations, we have discussed vanishing gradient, and tan h is also computationally expensive, guys. The reason behind it is it uses this e power. What is e? Exponential. Exponential of the value should be calculated. So that is why it is computationally expensive. Later on, our researchers and the scientists decided to come up with an activation function which will address this vanishing gradient problem, and it is called ReLU. It is ReLU, rectified linear unit function. Let me show you the plot. Yes. Rectified linear unit function. And this is the plot of ReLU, guys. If you see here, till 0, it is a straight line on the x-axis, and you see a straight line, a diagonal line, which takes the values as y is equals to x. So ReLU uses a function. The formula for ReLU is given as max of x comma 0. So if x is greater than 0, obviously ReLU returns x. But if x is less than 0, ReLU returns 0. So I can see, the range of ReLU is 0 comma infinity. Can I get a range value less than 0? Impossible. No. For sure, the output, the range of ReLU will be 0 comma infinity. So what are the advantages when we use ReLU is, the first and the foremost advantage, the vanishing gradient problem that we have with both sigmoid and tan h functions was solved by ReLU function, was solved by ReLU activation function. And it is not computationally expensive. The reason is very simple formula. Max of 0 comma x. Nothing but calculating the maximum value. Is it an computationally burdened problem? No. And where do we generally use ReLU is, we use ReLU in hidden layer neurons as an activation function. But the problems with ReLU are dying ReLU. Because of this ReLU activation function, what happens is some of the neurons get dead. Why? Because ReLU, the range for the ReLU function is 0 comma x. Obviously, if x takes 100, the output will be 100. x takes 500, the output will be 500. If x is -1, the output will be 0. So, if we pass any negative values to this ReLU activation function, what will be the output from ReLU? It will be 0. So, because of this, what happens is, this 0 will be passed to the next layer. This 0 will be passed to the next layer. So, from there, the neuron gets dead. Because 0 multiplied with any value will be 0. And ReLU is not zero-centered case. So if you take the derivative of ReLU, if you see the derivative of ReLU, for x greater than or equals to 0, the derivative is 1. If x is less than 0, the derivative is 0. Right? So these ReLU is actually solving the vanishing gradient problem. Okay. But the problem with ReLU is dying ReLU. The neurons get dead whenever the output from ReLU is 0. So that is why, the variants of ReLU got introduced. The first variant of ReLU that got introduced is leaky ReLU. It is leaky ReLU. Instead of keeping the formula as 0, x, they just made a changes. A modified version of ReLU is leaky ReLU. What do you observe here? Max of 0.01x. The formula for ReLU is max of 0, x. But here we just added a coefficient for x. It is a very small coefficient, 0.01 into x, x. So the output will be 0.01, right? And x. If x is infinity, it will be infinity. If x is 1, this will be the value, 0.01. I hope it is making sense, guys. Even if you observe the plot, for ReLU it is like this. Since there is a small deviation in the curve, so we are going with to the downside for leaky ReLU. We are going in the downside for the leaky ReLU. So this leaky ReLU, fixes the dying ReLU problem. It fixes the dying ReLU problem. And it is also maintaining the computational efficiency. Yes, because this is not a hectic task. It is not a burden for us to calculate these calculations, right? But the limitation for leaky ReLU is it is also not zero-centered. No, it is also not zero-centered. So leaky ReLU is solving the problem that we have with ReLU. It is nothing but it is fixing the dying ReLU problem. Very important. The formula that leaky ReLU uses is max of 0.01 multiplied by x, x. Right? Let us understand one more variant of ReLU. It is called ELU, exponential linear unit. So if you see here, the plot is similar but with a curve. You'll observe a curve here. Instead of a straight line, you'll observe a curve. So this exponential linear unit uses exponential function. It uses exponential function. So if you see, the function is given here. X greater than 0, the output will be x. But if x is less than or equals to 0, this will be calculated. Okay. So what is the purpose of ELE is it helps us for improved learning dynamics. Yes, It helps us faster convergence. We can converge very fast. Then for smooth gradient, even if there are for negative values, the gradient will be very smooth. And the dying ReLU problem gets fixed? Yes. But the problem that we have with ELU is exponential linear unities. It is computationally burdened, guys. Why? We are using this exponential component. This part is included in the formula. So as we are using this exponential component in the formula, it is expensive. Either if you compare with ReLU or leaky ReLU. There is one more activation function that need to be discussed, because so far whatever we have discussed, it might be ReLU, leaky ReLU and ELU, all of these activation functions are preferred. We'll be using them in hidden layer neurons. Within the hidden layer, we'll be using these activation functions. But the last activation function that we are going to discuss is softmax. What is the purpose of softmax activation function is, we use softmax for multi-class classification problems. Assume that I am working on a classification problem which has multiple classes. Okay. So in the output layer, we use softmax activation function as an activation function for, predicting the output. And softmax uses this formula, exponential value calculated by overall exponential values. The range of softmax is again between 0 to 1. So it will be similar to sigmoid. It will be similar to sigmoid because the range is same 0 to 1. But the difference between sigmoid and softmax is, sigmoid is used for binary class classification problems. Softmax will be used for multi-class classification problem. And when you are trying to use softmax, okay, these are your values that you get. If I use softmax on these values, all these values, will be normalized. They will be normalized. When you normalize, when you take up sum of all these values, it will be 1, guys. Even try calculating, summing up all these values, it will be 1. Okay. But the limitations with softmax are, they are computationally burdened, because we are using again that same exponential component in the formula of softmax. It is computationally expensive. And it is sensitive to outliers as well. If you are going to use any structured data, yes, gone keys. So I have to be very careful with respect to the outliers. So these are the different types of activation functions that we have, okay, as part of these neural networks. Okay, within the neurons, we are supposed to use activation functions. Why? Without these activation functions, the equation that we get is similar to a linear regression case. And these activation functions add non-linearity to our neural network. Now let us understand what are loss and cost functions. What are loss and cost functions? Very important. Loss function is nothing but the difference between, actual and predicted. The difference between actual and predicted of one single training example. Okay, assume if there are 100 rows, guys. In my data set, if there are 100 rows, I'll pass the first row values. Yes, when I pass the first row values, my neural network will produce some output. Yes. So the predicted value and the actual value, both I have, right? I'll calculate loss. So the loss, the error This is also called as error function. The error between the actual and the predicted value for one single training sample is called loss. Then what is called cost? Cost is the same but for the entire data set. If you are doing the same thing for the entire data set, it becomes cost. So in short, cost is nothing but aggregating the loss function values. If I pass the entire data set, what I'll get for each and every row, I'll get the loss calculated. Yes. When you aggregate all these loss values, you'll get cost. See, that is what I'm doing here. The formulas. Okay. So if assume that there are n rows. So sum up all these n rows divided by n will give me the cost function value. This is also called as objective function. Loss function is called as error function. Cost function is called as objective function. So in general, we'll have two problems. What are they? Regression and classification. If it is a regression problem, we can use mean squared error or mean absolute error, squared error. So the error gets squared. Since there are n number of samples, n number of records, sum up all the squared errors, then calculate the mean. So that becomes mean squared error. The same one more metric that we have under regression problem is mean absolute error. Instead of squaring these errors, calculate the absolute value. When you calculate the absolute value, mod of minus x is x. So even though if the error is negative, you'll get a positive error. Right? So either I can go with the mean squared error or mean absolute error. What in case of classification problems? We use cross entropy loss, also called as log loss. This is for binary class. Binary class, if there are only two classes, we go with cross entropy loss or log loss. If there are multiple classes, we go with categorical cross entropy, where C represents the number of classes. And guys, you need not memorize these formula. Just memorize these metrics, the terminologies. For binary class problem, we go with log loss or also called as binary cross entropy. For multi-class problem, we go with categorical cross entropy loss. Making sense? Yes. Now, let me start. What are these optimizers? There is a concept called optimizers, and one of the widely used optimizer is gradient descent. We'll be understanding gradient descent as well, guys. So focus. The purpose of optimizers is as part of, forward propagation, you'll get loss calculated, you'll get the predicted value, and once after getting the predicted value, as we have actual, we calculate loss. Loss also gets calculated. Once after calculating this loss, our aim is to minimize this loss. In order to minimize this loss, the weights and bias has to be updated. Why? Because these weights and bias got initialized randomly. Right? So when I update the weights and bias that got initialized randomly, the loss gets reduced. But how can I reduce these weights and bias? Using optimizers. Optimizers are nothing but, they are again algorithms. They are algorithms which help us to update the parameters, weights and bias. Okay. And they work in such a way that they help us to minimize the loss. Making sense? Yes. So these optimizers, they also help us to adjust the learning rate, the eta that we have earlier decided. Okay, so this eta value gets adjusted dynamically. Okay, it avoids local minima and it also speeds up the convergence. So how fast this loss has to be reached the global minima will be decided by the optimizer. Okay, and it also handles the issues like vanishing gradients. Okay, so one of the widely used optimizer is gradient descent, guys. We are going to understand gradient descent, how gradient descent works as part of this session. Okay, so in gradient descent, it is an optimization algorithm. Okay, optimization, which is working to minimize the loss function. The loss function will be minimized in such a way that the loss will be moved to the steepest descent. The global minima value has to be achieved. Okay, so how can we achieve that? When we update the weights and bias. When we update the weights and the bias that got initialized randomly, and this, when we do it for multiple times, which are called as epochs, then we can achieve the lowest loss function. Okay, so let us understand what is the process of gradient descent. See, the same process, whatever we have discussed, how neural network works in the same way, it initializes parameters, both weights and bias. Yes. Then post initializing these parameters, you'll get the prediction done. Once after you get the prediction, we calculate the loss. Yes. So you take any of the loss function and you calculate the loss. Once after calculating the loss, we also calculate the gradient of the loss. What is the gradient? Dou L. Okay. Dou L by dou W. If this is for weights, if it is for bias, dou L by dou B. B represents bias. And once after these gradients got calculated, we'll update the parameters using the formula W new is equals to W old minus eta multiplied by dou L divided by dou W old. Dou W old. So when you use this formula, what happens? The new weights gets calculated, and taking these new weights, again the model starts propagating forward. So this process will get continued till where? Till a certain number of epochs, which help us to achieve the global minima. What is global minima? From starting we are discussing global minima, right? One more minute, guys. You'll understand what exactly is global minima. Okay. And finally, it checks for convergence. It stops the algorithm once the loss improves. If the loss is not improving, then the algorithm stops. Then, once it also reaches the maximum iterations, it stops. If the change in loss between the iterations is below a predefined threshold, okay, within the threshold only, if you see the change in the loss, the model stops. So, if the convergence is met, yes, gradient descent stops, guys. And the best weights, the parameters, weights and the bias values will be saved. Let us visualize it, because everything we have it in, the flow, but let us visualize it. You'll get the clear idea. If you see here, this is what I was talking about from earlier. Okay. So on the x-axis, what do you have? weights. On the y-axis, cost or loss function. Either, whatever it might be. Initially, okay, this is the curve that you see here. It's a parabola. Yes, and this point is called, global minima. Let me change my color. Right. So this point is called global minima, and we are supposed to achieve this point. So assume that initially the weights that got initialized, okay, so here the weights were initialized here, okay. So we might also calculate loss or cost. Yes. So if you see here, the cost or the loss function is very high. The weights being here, how is the cost? The cost is very high, or the loss function is very high. Okay. So using the formula, what is that formula? W new is equals to W old minus eta multiplied by dou L by dou W. Using this formula, it has to achieve to this bottom, because the cost function or the loss function should be very less. So throughout this entire graph, where do you see the smallest value for loss? Here? Yes. But when can you achieve it? When the weights updates. When the weights and the bias get updated, only then you can achieve this point. How can you update the weights? How can we update the bias? Is using optimizers. We use optimizers. And because of these optimizers, we see the model gets converged. Okay, wherever the weights might be initialized, our final aim is to achieve the minimum cost, the global minima value. And that can be achieved using optimizers, guys. There are multiple optimizers. We have Adam optimizer, RMS prop. Okay. Under gradient descent itself, we have three different types of optimizers. Okay. So let us understand all these three different types of optimizers one by one. The first one is called batch gradient descent. The second one is called stochastic gradient descent. And the third one is called mini batch gradient descent. So what is the difference between these three? When we say batch gradient descent, it means the entire data set will be used for every iteration. So assume I'll take an example. If there are 100 rows and some X columns or Y columns, okay, but I just want to, my focus is on number of rows. Okay. So in case of batch gradient descent, the entire data set, nothing but the entire 100 rows will be used for every iteration. And when it is used? In case of small data sets. Why? If you have large data sets, it will be a computationally expensive. Then coming to stochastic gradient descent, we use stochastic gradient descent in such a way that it uses only one training sample. That means only one record will be passed at a time. So that means it will update the weights for every record. See, it updates the model parameters after each individual record. But here, for 100 records, the model parameters will be updated only once. But here, 100 times you are passing, right? So the model parameters will be updated for 100 times. What about mini batch? Mini batch is upfront defining the batch size. Defining the batch size upfront and Accordingly, we'll be passing the number of records. If I say I want to pass the data in 10 batches, so how many records will be passed at a time? 100 by 10. So that means 10 records will be passed. If I pass 10 records, 10 records, 10 records, so that, in 10 batches, the 100 records will be passed. After each and every batch, the model parameters will be updated. So that means it updates the model parameters in this case for 10 times. And when it is generally used in case of large data sets, and this is what we implement also. We'll go with mini batch gradient descent only, guys. The reason behind it is, if I'm working on real time, I'll have multiple records, millions. I'll upfront define the mini batch size. Then I'll go with, I'll just pass such the n number of records. Clear? Yes. So these are the overview of gradient descent variants. There are multiple types of optimizers, because as we don't have time, we are not going to the depth of optimizers. Okay. Let us finally understand the types of neural networks. As we have understood, the neural networks is the base. Neural networks is the base. For the entire deep learning, we have single layer perceptron. This is the basic one, in which you'll have only one hidden layer. Okay, single layer perceptron, multi-layered perceptron, multiple layers, feed forward neural networks, CNNs, convolutional neural networks, which are designed for image data. They work well for image data. Recurrent neural networks, which work well for sequential data like time series, then text. Okay. The updated version of RNNs is LSTM, long short-term memory networks. Okay. So the updated version for again LSTM is, we have GANs, autoencoders, transformers. All of these are types of neural networks only. They are types of neural networks. So either if you want to learn transformers, encoders, or GANs, whatever it might be, even RAG, yes, you have to learn neural networks. If you don't learn neural networks, you cannot, ANN, because ANN covers everything. Okay, if you don't understand ANN, you cannot understand the rest of the neural networks, because every other neural networks, the other types are built on top of ANNs. I hope it is making sense. So without delaying, let us quickly, implement ANN on a data set. I take a use case. So let me implement ANN on a use case. So what am I trying to do here, guys? I'm using ANN on rain prediction data set. Okay. So we are going to predict whether it will rain tomorrow or not. Okay. So for that, let me show you the data first of all. This is the data set in which we have, this data set is from actually, Australia continent. So we have location, minimum temperature, maximum temperature, rainfall, so on. There are multiple features. Humidity calculated at 3 p.m. Humidity measured at 9 a.m. Then rain today, whether it rained today or not. But our target column is rain tomorrow. Whether it will rain tomorrow or not is what we are trying to predict using ANN. So this is a structured data, right? You see structured data, right? So let us try implementing ANN for this data set. But I'm not proceeding with Spider. I'm not going with IDE Spider. The reason behind it is, as I'm going to use ANN, neural networks in the picture, it's better if I go and use GPUs. Okay, since my machine is not capable of GPU, I have chosen Collab. This is called Google Collab, guys. IDE that was provided by Google, and everyone can use it. The only thing is you should have a Google account. That's it. If you have a Google account, you can use this Google Colab. What you are supposed to do? Log into your Google account and search for Google Colab. Okay, it will redirect you to the Google Colab, and you can start typing your code. The IDE that you see for Colab is completely different. It is not similar to Spider. It will be similar to Jupyter notebooks. You'll see cells instead of the scripting pane being plain. You'll see cells. Within the cells, we'll have the code. Okay, right. So this is our code, and here we have also provided the data set. Data dictionary was provided, and this data set contains 4 years of daily weather observations from multiple Australian weather stations. Okay, so what I'm going to do here is I'm going to install a package. Okay, so when it comes to Google Colab, whatever the packages that you don't have, you're supposed to install it. And before that, before starting executing your code, you see runtime. Under runtime, you'll have change run type option. So when you click on this change runtime type, by default it will be select CPU, you change it to GPU, guys. Okay, when you select GPU, the execution and all will be very fast. Then click on save. Okay, now let me start installing the required packages. So I don't have feature engine, I'm installing it. The same command pip install feature, pip install the package name. And since I'm using collab, I have to use exclamatory mark. See, so it installs and it gives the message. So successfully it installed the package and the version is 1.8.3. Right. Next to it, what am I doing? I'm importing the required libraries. Whatever the libraries that are required for me, I'm importing them. Pandas for data manipulation, Winsorizer for handling outliers, simple imputer for imputation, one hot encoder for encoding, standard scaler for feature scaling, train test split for splitting the data into train and test splits, partitioning the data, and warnings. Warnings is to filter the warnings, to surpass the warnings that we get. So I'm importing all these packages. Done. See, you'll just get this tick mark is. When you click on this play button, you'll get this tick mark. So that means that particular cell got executed. So it is done. Now, I want to read the data set. Instead of having the data in the local machine, you should also upload this data, whatever the data that I have earlier shown, this data set, you should also upload to this IDE. How? On the left side, on the left side bar, you see a folder kind of icon, files. If you just click on these files, you'll see again options. The first one is for uploading to the session storage. The first option is for uploading. Click on it and navigate to that particular location. See. So this is what I want. I'll click on open. After uploading the data, See, the data got uploaded. Then you click on these three dots. You'll get multiple options again. Click on copy path and you can close it. You can use that path here, guys. That path need to be passed. See, I'm passing the path of my CSV file. But this is not the path of the CSV file from the local machine. Okay, within the session, you are supposed to upload this CSV file, whatever the file might be. Okay, so I'm reading the CSV file using read underscore CSV function. And where am I storing the data? In the variable df. So df will become a data frame. And I would also like to get the dimensions of the data. So I'm using shape attribute. So df.shape will return me the dimensions of the data. So let me execute this. So you see the results. Is that a huge data? Okay, is this fine? 2,54,358 records and 19 columns. Right. Next to it, I'm going to check the missing values in the data. What is the logic that we have? Is null.sum? Yes. And I'm storing the results in missing underscore values. When I say print of missing underscore values, this will return me the missing values in the data. See. So apart from location column, in all the columns, there are missing values. There are missing values. Then what am I doing next to it, guys? Try to understand the code. I want to drop, I'm using drop NA function, which means to drop the null values, the missing values, but based on one column. What is that column? Rain tomorrow. In the output column also there are some missing values, right? So which is not accepted. What am I doing? I'm going to remove these missing values. I'm going to drop these records in which we have in case of rain tomorrow column. And where am I storing the results? In a new object df underscore cleaned. So I'm also performing isNull.sum on the same data frame. So for rest of the columns, you'll observe the missing values. But for rain tomorrow, it will be 0. Why? Based on this column, I have removed the missing values. Next to it, value underscore counts. What does value underscore counts function does? What does value underscore counts function does? Value underscore counts function will identify the unique categories and it will also return the count of each and every unique category. But on which column I am doing it? On the Y column, rain tomorrow. So I can observe that for no category, it is around 1,92,000. The count is 1,92,000 and for S category, it is 54,535. Right? Then what am I doing is I'm filtering the rows. I'm filtering the rows, all the rows of no. Okay, within this rain tomorrow, I have two categories, no and yes. So the rows belonging to no will be part of no underscore rows, and the rows that are part of yes. If the rain tomorrow column has yes, those records will be part of yes rows. Why did we filter? We'll understand. We'll understand. Instead of taking the entire data set as it is, it's better if I go and work on the random sample of it. A sample of it. Right? So what am I doing is, I'll take a 22,000 rows from no rows and 30,000 rows from yes rows. I'm taking a sample of 22,000 rows from no rows and 30,000 rows from yes rows, data frames. And I'm using random underscore state is equals to 42 for reproducibility. Whenever I run the same code, in order to get the same sample of records, we have to stick to a int value for random underscore state. So that value I'm going to keep it is 42. And once after getting these rows, I'll concatenate both of them. I'll combine no sample and yes sample data frames using pd.concat function. Okay, then next to it, once after concatenating these rows, I'll also shuffle the rows. This is my final data frame, right? So within this data frame, what I'm doing is I'll take the sample function and I'm defining a fraction, okay, to shuffle these records. To shuffle them, I'm taking a fraction of 1 and random underscore state, I'm keeping it as 42 for reproducibility and resetting the index. Done. Now, I'll cross check the results by performing value underscore counts on the y column right tomorrow, because yes should be 30,000 and no should be 22,000. That is what we have defined. Instead of working on the entire data, we finalize to work only on a sample, right? Yes. So that means in total 52,000 records and 19 columns. Now let me perform the top records. In order to display the top records, we have head function. Head function will return me top records by default 5. So if you see here, this is my data set, guys. The location, min temperature, max temperature. So this is quite opposite to, spider. There is no kind of variable explorer tab, plots tab, no, nothing. No paints. You'll just, find only the cells. Within the cells, you are supposed to keep your Python script. Then, what does info function does? What does info function does? Info function will return me the complete information of the data set. So I clearly understand that there are missing values. Yes, there are missing values apart from location and rain tomorrow. In all other columns, there are missing values. Dot columns attribute will return as the list of columns. So these are the list of columns that we have within the data frame. Then I'm dropping the unwanted column, that is location, which is not required for us, because location is like an identity, guys. Location is like an identity which is not required. So I'm using drop function. Okay. From the data frame, I'm dropping the records. I'm dropping the column location. I'm specifying axis is equals to 1. When I say axis is equals to 1, it means location is a column and in place is equals to true represents. It is an in place operation that we are performing. Done. Next to it, I'm splitting X and Y. I'm splitting inputs and output. How? From this data frame, if I drop the Y column, it will return me inputs. And if I consider only the Y column, it will return me output. Done. So fraction of seconds, each and every cell is being executed. Right? Then I'm also checking for the null values, whether there are null values or not. In both inputs and output, I'm checking the null values and I'm printing the results. Yes, there are null values in the inputs, but there is no null value in the output, 0. Output doesn't have any null values, no. So let me focus only on inputs for time being. Okay, so I'm splitting categorical and numerical features within the inputs. Okay, I'm using select dtypes function. We using this select dtypes, I would like to include only int and float values. I would like to include only int and float values. So this will include only the numerical features, and the next line of code will include only the categorical features, and I'm printing both of them. So within the X, within inputs, all of them are numeric. There is only one column which is non-numeric. It is rain today. Rain tomorrow is output, guys. Rain today is part of input only. Under input, it is again a categorical feature. Then I'm going to check the missing values in the categorical features, whether there are missing values or not. Yes, there are 731 of them are missing values. Right. So let me use simple imputer strategy. Let me use simple imputer strategy because in order to impute the values, we use most frequent, nothing but mode strategy to impute the values. So I'm using mode, most underscore frequent. I'm initializing simple imputer function, and this simple imputer function post initializing, I'm using it on the categorical features, nothing but rained today column. I'll make it to fit on the data. I'll get the transformed results. These transformed results will be stored to a data frame. This will be an array actually. This array I'll convert back to a data frame by passing the columns from the previous categorical features underscore dot columns. And finally, I'm checking whether there are missing values or not post applying simple imputer. See, 0. That means mode imputation was being done. Then I'll also perform one hot encoding. I'm going to perform one hot encoding. What does this one hot encoding does? It actually performs, it converts the non-numeric column to numeric column, guys. So I'm initializing one hot encoder. I'll make it to fit on the categorical columns, categorical features. I'll get the transformed results. These transformed results, I'm storing it to an object called encoded underscore features. This will be an array. This array I convert back to a data frame by passing the column names. I'll get the column names from the categorical underscore features underscore inputted, and this will also return the index values. And finally, I would like to get the top 5 records using head function. So I can understand the encoding was being performed. Earlier, under rain today, we have no and yes, two values. But here, I can clearly see under rain today, it created me two columns. Encoding was being done. Now, let me focus on the numeric columns. So far, we just focused on categorical columns under inputs. Now, let me focus on numerical columns. So, checking for missing values. Yes, there are missing values. But before performing imputation, it's better if we go and visualize box plot. What is the purpose of box plot? The purpose of box plot is, it gives the information about the presence of outliers or not. So I'm using the box plot code, and this will return me the box plot for all the columns at a time, guys. See. So I see outliers in all the columns. In all the columns, there are outliers. See, right? So what I'll do is, I'll go with median imputation. I'll go with median imputation. Why? The reason behind it is, we have box plot. When I visualize box plot, there are outliers. So as we know, outliers, mean gets influenced by outliers. I'm just going with median strategy. I'm going with median strategy. Focus. So within the simple imperator, I have kept it as strategy median. So this initializes simple imperator. Then next to it, I'll make this simple imperator fit on the numerical features. I'll get the transformed results. These transformed results will be stored to numerical underscore features underscore imputed object, which will be an array. I'll convert this array object to a data frame. And finally, I'm checking for the missing values again. So median imputation was being done for the numeric columns. Let us check for outliers again. Post imputation, whether we have outliers or not. Yes, still there are outliers. Still there are outliers. So now when I am trying to use winsorization, okay, in order to treat all these outliers, I am going with winsorization, where I'll keep the method as Gaussian. I'll keep it as Gaussian. So in case of Gaussian, it uses the formula mu plus or minus 3 sigma. Okay, so I would like to treat the outliers at both the ends. I'll go with the fold 1.5 and the variables are the list of all the numeric columns. So I'll initialize winsorizer. This winsorizer will be made to fit on the data and I'll get the transformed results. These transformed results will be stored back to a object. On this data frame, again I am plotting a box plot to visualize whether we have outliers or not, guys. See, in all the columns, I don't see any outliers, but only in 1, 2, 3 columns. Okay, here we have 2 and here in 3 columns I see outliers. Assuming that these outliers are genuine, I'm proceeding further. Okay, I'll perform feature scaling. In case of feature scaling, I'm initializing standard scalar and I'll make it to fit on the data. I'll get the transformed results. These transformed results we are storing to clean underscore numerical. Okay. So once if you get the transformed results, it will be an array object. I'll convert back to a data frame. So this is the output of, the standard scalar. I'll concat the final results. I'll concatenate both the numeric and the non-numeric outputs using concat function. Okay, along the axis, and I'll get the head. The top 5 records is what I'm trying to get. See. So these are my final columns. If you see here, all the values got scaled. There are no big values. All of them got scaled using standard scalar. Within the Y column, within the Y series, we have 2 different categories, yes and no. So I'm mapping these values, yes with 1 and no with 0. So when I try to map with these values, the values for S will become 1 and the values for no will become 0. Done. Now I'll go and perform train test split, guys. So far we just performed data pre-processing only. Okay, we did not start model building. Now let us start model building, but before that we have to split the data. Yes. So I should pass both x and y. What is x? X is nothing but final features. Final features are nothing but this, the concatenated results. Okay. So I'll pass both final features and the y column, the y series, where the test size I'll pass it as 0.2. So that means the test will be 20% and the train will be 80%. To produce the same samples into both train and test, we are using random underscore state parameter, and I'm passing the value for random underscore state as 42. Done. Now we'll get four different objects, four different objects. They are x train, x test, y train, y test. Okay. Now what I'll do is I'll import the packages that are related to, the neural network, because we have to define a neural network. We have to build a model, right? So for that, we have a package called TensorFlow. There is a package called TensorFlow. For building the neural networks, deep neural networks, we use TensorFlow, guys. So I'm importing TensorFlow as it is as TF. Then from TensorFlow.keras.models, I'm importing sequential to build a sequential model. Okay, sequence of layers of model. I'm importing sequential. Then from same TensorFlow.keras.layers, I'm importing dense and dropout. So this dense is a layer, which helps us to create a fully connected neural network. And dropout is a regularization technique which helps us to prevent overfitting. So how does they work? You'll understand this. And from optimizers, I'm going to use Adam optimizer. Okay, to update the parameters, I'm using Adam optimizer. From callbacks, I'm importing early stopping. Again, early stopping is a hyperparameter which helps us to, it's a regularization parameter which helps us to, stop the training. Okay, it stops the training based on a certain condition. And finally, from callbacks, I'm also importing reduce learning rate on plateau. This will reduce the learning rate. So the neta value that we have discussed, yes. So I'm, importing all of these, done. Now let us understand, guys. So this is the code for the entire neural network. Focus, because so far whatever we have discussed, you guys have good, picture on the previous code, because we have discussed that as part of data pre-processing, KN and so on, right? But this is something we are going to learn for the first time. So when I say model is equals to sequential, sequential will allow me to build a layer by layer model. Okay, it will allow me to build a stack of linear. See, it groups a linear stack of layers into a model. So that layers I'll define one by one. The first one, see, model dot add. I'm adding to the model. What am I adding? A dense layer. Okay, so what is this dense layer does is, it allows us to build a fully connected layer case in which the number of units are 64. What does this units means? The neurons. Units means the neurons. How many neurons? 64 neurons. Activation function that I would like to take is, in these neurons, I would like to go with ReLU. I would like to go with ReLU. And input layer, we should also have input layer. Yes. So the input dimension that we have is 18, which means 18 nodes will be created as part of input layer. Okay. So this becomes my first hidden layer. Okay. So visualize the neural network. In the input layer, we'll have 18 nodes, which will be connected with 64 neurons of first hidden layer. Within this first hidden layer, the activation function will be ReLU. And between these input layer and the first hidden layer, I'm adding a dropout layer. What is this dropout? It is actually not exactly a layer. It is a regularization technique, okay, which helps us to prevent overfitting. What does this dropout does is, this dropout drops 20%, 0.2, right? 20% of the values from the previous layer. What is the previous layer? It is nothing but the input layer. Yes. So it randomly drops 20% of the values. The node values will be dropped. Then coming to the next layer, I am adding one more layer. Yes, what kind of layer? It is again a dense layer. It means a fully connected layer. How many neurons in it? 32 neurons, which means the second hidden layer contains 32 neurons. What is the activation function? ReLU. Should I keep again input dimension? Not required. Input layer will be only one case, but we can have multiple hidden layers. I am again adding the dropout. How much? 20%. So 20% of the neuron values can be dropped. Again, I am coming up with third hidden layer in which I'll have 16 neurons. Activation function is ReLU. So input layer in which I have 18 neurons. The first hidden layer has 64 neurons with ReLU. Second hidden layer has 32 neurons with activation function ReLU. Third hidden layer will have 16 neurons with activation function ReLU. How many hidden layers? 3 hidden layers. And finally, I am adding again, only one layer. I'm adding a dense layer in which it will have only one neuron. What does it mean? It is an output layer. Activation function is not ReLU, sigmoid. Why? The output is binary, either yes or no. The neural network has to predict whether it will rain tomorrow or not. So it is binary. So I'll go with sigmoid activation function. What if I'm working on a multi-classification task? The activation function will be softmax guys. Okay, so that is how we change these activation functions. And finally, once after defining the model, we make the model to compile, to run using the optimizer Adam. I'm using Adam, one of the optimizer, where I'll specify the learning rate as, so the neta value I'm defining, and I also want to consider binary cross entropy. Okay, for binary classification task, binary cross entropy or log loss is what we check. The cost function. And metrics I want to consider is accuracy. Okay, and when I say model.summary function, this will return me, the entire summary of our model. See, with this table, when you say model.summary, it returns this table. What does this table contains? The table contains the layers, the output shape, and the number of parameters at each layer. And the total parameters. Total parameters is nothing but sum up of, when you sum up all these values, you'll get the total parameters. But let us understand this table. This table is very important. If you understand this table, you can visualize that neural network in your mind. Okay. So in short, I'll draw the visualization of the neural network here. I have, sorry. So I have input layer, How many nodes? 18 nodes. And all of them are connected to hidden layer. The first hidden layer contains 64 neurons. So on. And all of them are connected to all of the neurons. The nodes are connected to all the neurons present in the first hidden layer. And the second hidden layer contains 32 neurons. These are 32. And in the same way, all of them are connected because I'm using dense. When I say dense layer, all of them will be connected. A fully connected layer, neural network is what we see. Okay. Then the third hidden layer contains 16 neurons. Again, the same. And finally, one output layer. Output layer in which you'll see one neuron. So this is our neural network, guys. As I cannot draw 64, 32, 16 neurons, I'm just representing with, the dots. So if you, memorize this neural network in your mind, in your brain, okay. So in these hidden layers, what am I using? The activation function ReLU is used. The function ReLU. What is the function of ReLU? 0, x. But in the output layer, the activation function that I'm using is sigmoid. What is the function? 1 by 1 plus e power minus x. Okay. Now let us try to understand this, table. So the first dense layer, it says 64 neurons. So that is why you see 64. But coming to the weights, how many weights will be initialized? Just memorize. We have also already understood. By taking a small neural network, we understood the weight parameters, the weight matrix. So when you multiply these both, 18 multiplied by 64, you'll get some number. 18 multiplied by 64 will return you 1152. 1152. So these many weights will be initialized between the input layer and the first hidden layer. But I see a different value. Hold on. To this, you should also add bias. How many bias values will be initialized? 64. So when you add 64 to this value, it will be 1216. It will be 1216. That is what you see under parameters. Dropout is not a layer. In the sense, it is a regularization technique which helps us to drop the values. Come to the next dense layer. If you again multiply 64 with 32, you will get some number. To that number, you add 32 again. That will return you 2080 parameters. Why 32? Why 64 we are adding? These are bias. These are weights. For 64 neurons, 64 bias values will be added. For 32 neurons, 32 bias will be initialized. Okay, even if you observe in the last layer, how many weights will be assigned? 16? Between 16 neurons, and when you multiply 16 with 1, 16 weights. How many bias will be initialized? 1. So 16 plus 1 is 17. So in this way, when you add all these values, you'll get the total parameters in the neural network. This is very important, guys, because majority of them, they'll not understand the table, the sequential model that we are trying to build, they'll not understand. So this is what you are supposed to focus. Done. We have initialized, we have defined our model. Now, I'll use the model, I'll make the model to fit on the data. I'll make the model to fit on the data. So what am I doing? I'll take X train, Y train, the train data I'm taking. Then the validation within this train data, I would like to provide a 20% of the data for validation. So 80% will be only used for train, 20 will be used for validation. And number of epochs that I would like to go with is 100. 100 epochs, guys. And batch size 32. What is the batch size? 32 samples. Okay. And when it comes to callbacks, I would also provide early stopping. What does this early stopping does is, it stops the model when there is, when it observes these. It monitors the validation loss, okay, with a patience of 25. That means within 25 epochs, what is an epoch? Epoch is nothing but both forward and backward propagation. One forward and backward propagation is called one epoch. Within 25 epochs, if there is no change with respect to the validation loss, we are saying the model to stop the training because there is no use. Right? Then restore best weights. So when it stops, instead of taking the last weights as default, we are going to restore the best weights. Wherever we get the best weights, those weights we are asking to consider. Okay, so I'm making it to fit the model. See guys, it starts, the epoch starts one by one. So epoch 1 is done out of 100 if you see. Epoch 1 out of 100 is done in how many seconds? 7 seconds. What is the accuracy? 74%. Validation loss on the train data 0.51. This is the validation accuracy 77. Okay. So this is how you can understand. For each and every epoch it calculates. But will it go for 100 epochs? May or may not. If this criteria is met anywhere, it stops in the middle. It stops in the middle. So just focus. Within fraction of seconds, it is completing. See, as the number of epochs are increasing, what's happening to the accuracy? If you see 78, 79, 79, okay, it is increasing. So, you see there is a change. Epoch 21. For each and every epoch, it is giving the step, the time, the accuracy, the train accuracy, the train loss, the validation accuracy, and the validation loss. It's under training. So when there is no change, it stops. Observe guys. Yes. If you see here, did it complete 100 epochs? No. It just stopped at 65th epoch. The reason behind it is, you know, what we have provided in the code, it has to stop. We used early stopping, which is a regularization technique, okay, which will monitor the validation loss. So these values will be monitored by the early stopping parameter that we have defined, and within the 25 epochs there is no change, it stops. If you see here, let me go with the last 25 epochs. See, if you see here, is there any change? 0.44, 0.44 in all the cases. See, so that is why it stopped. That is why it stopped. And now finally I'm going to get the final results. I'm going to check whether the model fit, whether we got a good fit model, that is nothing but right fit model or underfit model or overfitting model. So model dot evaluate, where I'm passing X test, Y test and verbose. Okay. So it takes X test. It passes the X test values. The inputs in the test data will be passed, where the model returns the predicted values. As I'm also passing the actual, both of them will be compared, and this will return me the validation, you know, the validation test loss and test accuracy. I'm printing both. 79% is what I get on test accuracy, guys. The test accuracy is 79%. In the same way, let me get the train accuracy, where I pass X train and X test. What are the results? It is 80%. So 80% on train data and 79% on test data. Obviously, we got a good fit model. That is what we can interpret. But the key important features that we have to understand here are early stopping is one. Then in the previous line of previous cell, yes, in this one, we are supposed to understand this summary table. If you are able to understand the summary table, you can visualize that neural network. Right? Yes. So this marks the end of ANN. Okay. So we are able to build a model which is capable of predicting 80% accurate results. The results are 80% accurate. And even if the results, if you compare both train and test, they are approx 80% on the train. The train accuracy is 80% and test accuracy is 79%. Right? Yes. So any questions? If you have any kind of questions, feel free to ask. I'll be answering all your questions, guys. And if you find the session went well, hit on the like button, do share across your connections. Thanks for your feedback, guys. Thank you so much. The feedback link has been provided. Please give your valuable feedback and do share across your connections and do subscribe to our channel. In future, we are going to come up with amazing content, guys. So do share across your connections. As a kind of encouragement, do support us. Hit on the like button. Thank you so much once again.